We'll quickly do some problems. Which of the following sets with the indicated binary operations are commutative rings? Okay, as you know, for us, rings are commutative with unity element. R1, the set of all matrices of the form A0, 0A with usual matrix addition and multiplication. So is this a ring? But we don't need uh, yeah, addition. You already said it's abelian group, right? Yeah. Distributivity, it's no problem. That is a property of the operation, right? Distributivity. So it does not matter which set of matrices you have, the distributivity will hold because it holds for the set of all matrices. So if you take a subset, it will still hold within that subset. It's not like closure or anything, no. So it doesn't depend on what set you take. It depends on the operation. Yeah. So yeah. So first, if A is a B is this matrix, and you add two of these, you will get A plus B 0, 0, A plus B. And if A and B are integers, then A plus B is an integer because the set of integers is closed under addition. This means A plus B is in the set R1. So closure is fine. And associativity or plus follows from matrix addition. From properties of matrix addition. That's also not a problem. Then the identity is 0, 0, 0. You also have additive inverse. Commutativity follows from commutativity in Z. Then for closure under multiplication, A times B is A00 A times B00B, which is AB00 AB, which belongs to R1 because A comma B belong to Z implies the product AB is in Z because multiplication is closed in the set of integers, or the set of integers is closed under multiplication. So this is closure under multiplication. Then 1001 belongs to this set because 1 is an integer. That is the identity. And matrix multiplication is associative in general. Distributivity is also a general matrix operation property. Then AB is AB00 AB, which is equal to BA00 BA, which is equal to B times A. So multiplication is commutative. As you can say, R1 is a ring. Okay, the second set is A00B, where A and B are integers. So in the first set of matrices, we needed both the diagonal entries to be the same thing. Here we can have different diagonal entries. We just need the non-diagonal entries to be zero, and the diagonal entries should be integers. Now, would this be a ring? This will simply be AC 0, 0, and BD. But AC and BD are also integers, so no problem. Closure is there, then this is also commutative because we can write it as CA00DB, and then that would be simply B times A. So there is no difference between having allowing different integers doesn't change anything. Properties still follow. So this is also a ring. Yeah. Uh, you can verify everything one by one if you are not convinced, but at least from the surface level, you can see that nothing really changes. So this is also a ring. In R3 is the set A10A. Is this a ring? Yeah, it's not even closed under addition, so it's not a ring, not closed. D is also similar. Yeah, same reason again. This is also not closed. So same reason holds here. Okay, then the next question is, um, which of the following statements are always true in any ring R? First statement is A square is equal to A for every A in R. No, A square is equal to A is not true. It doesn't. It's not necessary, right? If you 2 into 2 is 4, right? It's not 2. It's not saying A square is in R. It's saying A square is equal to A for every. But that's obviously not true from just from the counter example. Only the identity element will definitely have this property. E square is equal to E for every ring R. But other elements might not have that property. So we can't get. This is asking which of the following statements are always true in any ring R. So this statement is not always true. It's true for some values of A and not true for some values of A. So overall, it's a false statement. Counter example is Z plus multiplication. 2 into 2 is equal to 4. Is not equal to 2. Next statement is minus A times B is equal to A times minus B is equal to minus AB, or every A comma B belonging to the ring R. Is this true? Minus A means the additive inverse of A. My additive inverse of A times B, is it equal to A times the additive inverse of B, which is equal to additive inverse of AB? Is that true? Yeah, that is true. Uh, we can show this via the definition. So AB plus minus A times B is by the distributive property A plus minus A times B. But A plus minus A just by definition of minus A is 0 times B. 0 times B is 0. Now AB plus minus A times B is 0. We add minus of AB to both sides. Get minus AB plus AB plus of minus A times B is equal to minus AB plus 0. But minus AB plus AB on the left hand side, that will become 0 plus minus A times B is equal to right hand side, this is minus AB. So minus A times B is equal to minus AB. Similarly, you can show that A times minus B is also equal to minus AB. So all three are equal regardless of what value A and B are. So this is a true statement. Then C says for any A, B, C three elements in the ring, if AB equals AC, then B equals C. Is that true? It's always second. First operation will always call it plus. We'll always write it as A plus B. In rings, we'll always write it that way. In rings, right, this notation is the standard. There is almost nobody uses any other notation. It's only plus and into. And uh, yeah, uh, only in groups you can have plus into, you can have other symbols also. It's not that much of a hard and fast rule. It can change according to the group. But since here we have two operations, the notation is always plus and into. Always the notation is always into and plus. Yes, A inverse should exist. Ah, yes, but there's no guarantee. Yes. So for some A, B, and C, it might be true. For example, if you take A is equal to E, then obviously EB is equal to EC means B is equal to C. That's a redundant statement. It's a tautology. It's always true. So for some elements, it might be true, but we can't guaranteedly say that for all elements. So this is a false statement. The statement D is that minus 1 times A is equal to D minus A for every A in R. Is this true? Yes. Uh, Again, similar to part B, we just show that when you add minus 1 times A to A, you get 0. That means that minus 1 times A is the inverse of A, right? Minus A is the number. such that if you add to A, you get the zero element. If I show that minus 1 times A, when I add to A, I get zero element, then I'm done. So minus 1 times A added to A, we can write this as minus 1 times A added to 1 dot A because 1 dot A is A. So this will become minus 1 plus 1 dot A by distributive property. By definition of minus 1 plus 1 is 0. So this is 0 dot A. This will be equal to 0. Actually, this 0 dot A is equal to 0. That is also one property that I didn't really derive, but it's not directly from the axioms. From the axioms of the axioms of the ring do not state this, that the additive identity times any element is the identity is the additive identity itself. That we actually have to write a small proof for that. Yes, yes, that's it. You can simply write 0 plus 0 times A is equal to 0 times A, right? 0 plus 0 is 0. Then this by distribution is 0 times A plus 0 times A equal to 0 times A. Then you add the inverse of 0 times A, whatever it is, minus of 0 times A. Obviously, this will be 0 times A plus 0. This will be 0. Here, actually, in every step, I am using the properties. I'm not stating them. But these things might seem obvious, but they are not actually obvious. They only come because we have these properties. So here 0 plus 0 is 0 only because 0 is the identity element. And then we're adding the inverse of 0 dot A. That must mean, first of all, 0 times A must be closed. It must be in the group and then it must have an inverse. It's an additive inverse. So when you add the additive inverse, you get 0 on both sides. And then since that is the additive identity, 0 times A plus 0 is 0 times A. It's a very simple proof, but um, you have to be sure when you're doing these abstract algebra proofs, you just have to be sure that you're not using your intuition to write anything. You're using only the properties to write things. Because many times from you might write things out of intuition because it feels right, but you can't really do that. You must be sure that the result is coming from some property. Okay, so this is a true statement. Then the third problem is select all correct statements, similar to previous problem. First statement is the ring Z mod 11Z of integers modulo 11. Actually, I should write residue. Uh, I simply write this red mod. I don't like this because a lot of the times people call it the set of integers modulo 11, and they conflate Z11 with Z mod 11Z because as far as algebra is concerned, they're isomorphic, no? So they are considered to be the same thing, Z mod 11Z and Z11. But like I explained in last, I don't like seeing I don't like seeing it like that. It's true. It's not something wrong that they're doing. Because according to mathematicians, the two isomorphic objects are just the same thing with different names. But I still like differentiating between the remainders, which are just numbers, and the equivalence classes by the uh, one by the relation equivalence relation to two numbers are equivalent if the remainder is the same. So I'll just here it doesn't matter. The thing here is the ring Z mod 11Z has exactly 11 units. Is that true? First of all, how many elements does Z mod 11Z have? Yeah. So I mean, even if you consider the isomorphism, it's all numbers less than 11 and not negative, 0 to 10. So 11 elements are there, but a unit means elements having an inverse. Do all elements have an inverse in that? No, no, no. Unit. You say unit only when it's multiplicative inverse. That's why we have a specific name. It's called a unit if it has an inverse and a multiplication. See, we already saw one last class. I think we saw that Z mod 11, Z mod NZ, or simply Zn is a field if it has if n is prime, right? No, no, it's only a prime, not power of prime. No, no. The way we get fields with power of prime is different, not from integers. Yeah, only prime, exactly prime integers are obtained from Z mod PZ for some prime P. Yeah, yes, except 0. Uh, no, no, 10 it has an inverse, right? No, 0 doesn't have an inverse. Yeah, excluding 0, all the other things have inverses. And 1 and 10 are self inverses. So inverse of 1 is 1 and inverse of 10 is 10. Other things have unique inverses, I mean different inverses. They're not necessarily self inverses. Some of them might be. Uh, but 0 doesn't really have an inverse because what do you mean by an inverse? An inverse is some element such that A times A inverse is equal to 1. But Right now we saw 0 times A is 0 always. So regardless of what you multiply 0 with, you will always get a 0. You will never get 1. So there is no element such that 0 times that element is 1. Can't get 1 from 0. So 0 doesn't have an inverse in any ring or any group under multiplication. So except 0, since 11 is prime, all numbers have an inverse. That means there are 10 units. So first one is false, the second one is true. Then part C and D are pertaining to Z of I. Let Z of I be it's the ring of Gaussian integers. A plus IB, where A and B are integers. C says the element 1 plus 2i is a unit. And D says I is a unit in Z of I. Are they both true or both false? What do you think? One. Yeah. We already saw this. We showed that in Z of I, the only units are 1 minus 1, I minus I. By taking instead of 1 plus 2i, we took a number a plus ib. Then we said let c plus id be its inverse. Then we multiplied a plus ib into c plus id must be equal to 1. Um, and we actually followed through and used some neat tricks to show that at the end of the day, only I minus I, 1 and minus 1 have inverses. Yeah, you can go back to the previous lecture and see that if you don't remember. So this problem is mostly to refresh your memory on that, on these two things. That Z mod and Z, um all the elements other than 0 will have an inverse if n is prime. And Z of I only inverses, only units are 1 minus 1, I and minus I. So this is false and this is true. Next, select all the correct statements. Again, now only two statements. First one is if A comma B are units in a ring, then AB is also a unit. Part B says if A comma B are units, then A plus B is also a unit. Which of these is true? Yeah. So if C equal to A inverse and D equal to B inverse, then AB times CD or AB times DC is equal to A times BD times C, but D is B inverse, so this is A times C, which is A times C. But C is A inverse, so this is E. So DC is the inverse of AB. Therefore, AB is also a unit if A and B are units. But the second part need not be true. For example, in Z, in the ring of integers, 1 is a unit. So set A and B both to be 1. A and B are both units. It doesn't say A and B are distinct elements. You can pick the same element. A plus B is 2, which is not a unit. So the sum of two units need not be a unit. Then next question. Select all the correct statements. Statement A is at RB, the ring Z mod 4Z. Actually, we'll simply take this as Z4. At RB equal to Z4, there are non-zero elements in R whose product is 0. Is that correct? All Zns are rings. We saw that in one of the classes. Since it's Zn, the operation is multiplication and addition modulo n. So the product to be 0 doesn't necessarily mean that it is exactly 0. It could be a multiple of n. That would also be 0 under modular multiplication. So we saw in the proof of uh, Z mod nz is a field if n is prime. We saw if and only if n is prime. So we also showed that if n is composite, then it's not a field. And for that, in the proof, we use the fact that if it's composite, there is a factorization of n such that both the factors are not 1 and n itself. They are between 1 and n. So that they are elements of Zn and their product is 0. Z4 is 0, 1, 2, 3. But 4 is 2 times 2. So 2 times 2 is equal to 0 under modulo 4 multiplication. But neither 2 is not 0. So there are non-zero elements in R, 2 and 2. whose product is zero. So this is a true statement. Is that okay? Part B is statement B is the same thing except that now instead of Z4 it says the same thing about Z5. Now is this true? But that explanation didn't convince me. Huh. Why are they relatively prime? 2 and 4 are not relatively prime. Both belong to Z5. It only works for the prime number itself. It works for 5. It doesn't work for the other elements. If you just actually this can show this for any ring, um, any field. So Z5 is a field, right? So all the non-zero numbers have inverses, multiplicative inverse. So this property can actually be shown for any field, and this property is actually called. I mean, rings which have this property are called integral domains. So all fields are integral domains, but all integral domains need not be fields. The reason all fields are integral domains is because suppose you have AB is equal to 0 for two non-zero numbers A and B. What does it mean for two non-zero numbers? What is the property two non-zero numbers have in a field? What does every non-zero number have in a field? Yes, it has an inverse. So you can multiply on both sides by the inverse of the first element. Anything multiplied by 0 is 0. We already saw that. And A inverse times A is the identity. Identity times B is B itself. What does it mean? This means B is equal to 0. But what did you say at the beginning? You said A and B are both non-zero, right? If you said A and B are both non-zero, but we showed that B is zero if A is non-zero. So that's a contradiction. That means that both can't be non-zero. Okay, I'll define this integral domain. It is a ring in which For all A comma B in R, AB equals 0 implies A equals 0 or B equals 0. That means there are no two numbers that are non-zero that you can multiply to get a zero number. If you want to get zero, you have to, at least one of the numbers you are multiplying must be a zero. Ring is some structure that we have given, right, with some properties. An integral domain has additional properties to that. So set of integers is actually an integral domain. Not all rings have that property. For example, matrix rings. Of course, if you consider rings do not require the commutative property, then matrix rings are also matrix rings also exist, right? Then in matrix rings, it's not true that the product of two matrices is zero implies that one of the matrices must be zero. That's not true, right? There are non-zero matrices which you can multiply to get uh, a zero matrix, right? So it's this is an extra property, an additional requirement that some rings possess, not all rings. So it's one level higher. Uh, it's a higher abstraction than a ring. Then once you have an integral domain, if an even higher form of that is a field, where not just this property holds, uh, every non-zero element also has an inverse. Huh. No, there's no such thing as an integral. The integral is in calculus. There's no integral in. Ideal. No, no. Ideal is different from integral domains. Okay, that is entirely different. Ideals are the analog of the analog of subgroups. There are actually subrings which are exactly the analog of subgroups, but ideals are the objects of interest when it comes to rings. Uh, Similar to how subgroups are important when you are discussing groups, ideals have the same importance. They're not exactly the same. I will define them in later classes, but they have the same importance when it comes to rings. Yeah, this is not ideal. An integral domain is a ring. An ideal need not be a ring at all, according to our definition. Uh, in our definition, a ring must have the unity element, right? But a proper ideal will never have unity in it, so it is not a ring at all from our perspective. But an integral domain is a special type of ring. The integers are the one of the most important integral domains. Okay, so uh, the converse is not true. All integral domains need not be fields, but all fields are integral domains. We already know that Z5 is a field, so it is an integral domain. Um, but Z4 is not an integral domain. That we have to show separately by giving counter example. C is Z mod 4Z is a field and D is Z mod 5Z is a field. Now obviously this is false and this is true. Yeah, I told you, right? We don't power of prime fields, we don't get them from integers. You have to remember, only prime fields we get them from set of integers by doing modulo nz under modulo n arithmetic. That's only for prime fields. Fields with prime power size, we will get them from polynomial rings. You won't get them from integers. So Z mod nz is a field only if n is a prime, not prime and prime power. Fields can have only prime and prime power size, out of which the prime fields come from integers. Precisely Z mod pz for prime p. The prime power fields come from polynomial rings. See, I have not even explained how will you understand. We have not even come to fields, right? So that's why you won't understand. I have not explained it. We have not gotten there yet. We are still in rings. Then the next part is the units in R form a group under multiplication. Is this true? We already saw that if A and B are units, AB is a unit. So it is closed. Then the other property would be if B is in this group, then B inverse must be in this group. But that is also true. If B is a unit, B inverse is also a unit, right? Inverse of B inverse is B itself. So that's just true from how the ring is formed, how the group is formed. The group of units are all invertible elements in the ring. So if some element is in the group, its inverse is in the group. And we already saw in question 4 that if A and B are units, AB is also unit. So by that two-step subgroup test, it is a group. And F says the ring of integers Z has exactly two units. That's true, right? 1 and minus 1 are the only units. All other numbers don't have any multiplicative inverse in integers. Units means always multiplicative inverse. And then the ring Zi has exactly 4 units. This is also true. Just now we recalled that the only units of Zi are 1 minus 1 I minus I. So this is also true statement. This is more like a recap of things done in last class, but through problems. Then the final problem for this segment is, Okay, this is the definition. Let R be a ring. An element X of R is called nilpotent if x power n equals 0 for some natural number n or some positive integer n, because some people consider 0 also as natural number. We'll simply write positive integer to avoid confusion. So for some positive number, x power positive integer x power n is 0. If that is true, then x is called a nilpotent element of the ring. Then does Z mod 6Z have any? Of course, by this definition, 0 is a nilpotent element, right? Because 0 power 1 is 0. So 0 is always a nilpotent element of everything. So if you want to, you can actually even, according to your convenience, you can change the definition to mean that a non-zero element is nilpotent if x power n is equal to 0. We'll stick with this definition. So does Z mod 6Z have any non-zero nilpotent elements? What do you think? But 16 is what? Under mod 6. Yeah. So 4 square is 4. And 4 cube will be, yeah, yeah. So it keeps repeating. So 4 power n is 4 for anything, any n. So you can't get 0. 1, anyway, 1 power n is 1 for all n. So it can't be 0. It's not nilpotent. This is true in all rings. The multiplicative identity is never nilpotent. All non-trivial. Of course, we actually allow rings. We actually consider the zero ring to be a ring where there's just one element zero, and we say zero is the additive and multiplicative identity. Uh, but since that is a very trivial ring, we just ignore it all the time. So all these statements we make in this course will be for rings that are not zero. Okay, 1 power n is 1, so 1 is not nilpotent in any ring. What about 2 power n? 2 square is 2 cube would be, yeah, yeah. So it's either 2 or 4, power of 2. Then 3 square is, yeah, so 4 square is 4. What about 5 square? Yeah, so this is 1. That means phi cube would be, yeah, yeah. So you don't get zero. So it doesn't have any non-zero nilpotent elements. Whereas if you consider Z mod 4Z, 2 square is 4, which is 0. So 2 is a nilpotent element in Z mod 4Z. Okay, that's it for today. And tomorrow we'll start with homomorphisms. Homomorphisms of rings. Okay, I'll upload them. All right. Good night.